So hello friends, today we will start with the module 4 of optimization technique, and this module contains the topics unconstant optimization, that is method of STEPEST ascent descent, NR method, gradient descent, mini batch gradient descent, stochastic gradient descent. So these three is the totally theoretical based and these two is the numerical. Okay, so you can expect at least one question from this and two questions from this. Alright, so let's start with the STEPEST descent method. You have to follow these 4 steps in this method, and in detail we will see while solving a question. Let's go through it quickly. So start with arbitrary initial value. Any point you have to take at x1 and you have to set an iteration. That iteration can be 1, 2, 3, 4. Alright, so then find search direction SI. The formula for search direction is minus of gradient of Fi, that can be denoted as minus of delta F. Okay, so how to find the gradient that I have discussed in the first module, that is column matrix DF dx1 DF dx2 at point x1. And what is x1? X1 is the point you have chosen initially. Alright, determine optimal length lambda 1 star, then minimize the function at that point x1 plus lambda 1 star x1, and then after minimizing you have to differentiate this function at lambda 1 star. Okay, so whatever you get, then equate it with 0, you will get the value of lambda 1 star. Okay, then put the lambda 1 star value into the x2 equation and find the value of x2. Okay, so then find the gradient of f2, that is gradient of f2 can be given as df by dx1 df by dx2 at x2. Since you have to find the gradient of f2, so you will take x2 here. If you have to find the gradient of f1, then you will take x1 here. Okay, so this you have to match with the initial point. If that initial point is near to this value or it is equal to that value, then you have to conclude there itself, or if it's not, then you have to iterate further. Alright, so let's take an example and see it more better. Minimize function x1 x2 is equals to x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 square, starting from x1 is equals to 0, 0. See, initial position is given as x1 and this function is given. So first you have to find the gradient of f1, this f1. Okay, and how to find? You have to differentiate this function with respect to x1 first, then x2. Okay, so if you differentiate, you will get 1 plus 4x1 plus 2x2 minus 1 plus 2x1 plus 2x2, and you have to calculate for the gradient of f1. So you should have to take the x1 here. And what's the value of x1? x1 is 0, 0. So x1 is 0, 0. So small x1 is this 0 and small x2 is this 0. Okay, so put this respective value in this equation. You will get del f1 equal to what? Minus and 1 and minus 1. Okay, so then find s1. s1 is equals to minus of this all, minus of the gradient. Okay, if you do minus, then you will get minus 1 and 1. Okay, so after that you have to determine optimal step length lambda 1. So for that we minimize this equation. Okay, so how to minimize? F x1 plus lambda 1 star s1 you have to take and put all the respective value over here. Okay, f to f, then x1 is equals to 0, 0 plus lambda 1 star s1 you will find from here. Okay, so put same value here and then calculate it. How to calculate? Lambda 1 star into minus 1, that is minus lambda 1 star, and this is lambda 1 star. Okay, so this is the value, and take this as x1 and take this as x2. Okay, and same you have to put into this function also. Okay, put the minus lambda 1 star at the place of x1 and this lambda 1 star at the place of x2. Okay, then calculate the function with respect to minus lambda 1 star and lambda 1 star. Okay, then you will get this minus 2 lambda 1 star plus lambda 1 star square. Okay, then differentiate this with respect to lambda 1, you will get a point. Okay, the point as lambda 1 star equal to 1. Okay, then you have to find x2. As the procedure says, you have to find x2. x2 is equals to x1 plus lambda 1 star x1. So now you have all the values, then you can find x2 very easily. Then find the x2 value and then find the gradient with respect to f2, gradient of f2. Okay, then you will get df by dx1, df by dx2 at x2. So okay, so this differential you have solved earlier. Now you have to put x2 value. What is x2? Minus 1 and 1. You have to put x1 as minus 1, x2 as 1. So after putting the value, you will get minus 1 and 1. And now compare it with the initial value, that is 0, 0. So it is not close because it's a difference of 1 and it's not acceptable. Okay, so you have to move further for the second iteration, and likewise you have to do the same here. You have to find first the s2. Here we have find s1, so now you have to find s2. s2 is equals to minus of gradient of f2, that is equals to minus of this this one. Okay, so if you do this, you will get 1 and 1. Okay, determine optimal length lambda to, we minimize this. So then minimize the similar thing is there which we have done previously. Then now function becomes this, and you have x1 values as this, x2 value as this. Put the x1 x2 value in the function given in the question, this one, and calculate all the results. Okay, the result you will get as 5 lambda 2 square minus 2 lambda 1 minus 1. Now equate it with 0, you will get the value of lambda 2. Now find x3. x3 is equals to x2 plus lambda 2 s2, that is equals to minus 1 by 1, minus 1 1 plus 1 by 5 1 1. Okay, this you will get. So now compare this result after calculating all this. Compare this result with 0 0. It is not close anyhow. Okay, so you have to move to the iteration third, and likewise you have to do the same here also. Calculate all the values, then lambda 3 as this. Now you have to form x4, that is equals to this one, and find all the things. Now you will get 0.2, and 0.2 is like something similar to that 0 0. Okay, so you can stop here also, or else you have to, if you want, then you can move further iteration 4, or else you can stop because it's somewhat closer to that 0 0. Okay, so we can conclude that minus 1 1.4 is the minimum point to find f minimum, minus 1 and 1.4, and to find f minimum you have to put this minus 1 and 1.4 into that equation given, that function given. Okay, so you will get it as this as answer. Okay, so I hope you understand this question process, how to proceed with the answer. So practice it once, you will understand. Okay, so next is NR method. So let's see it with the same question. Same function is there and same starting point x1 is there. Okay, so to find x2 we have Hessian matrix. Now what is Hessian matrix? Hessian matrix can be given as J1 is equals to d square f by dx1 square and d square f by dx2 square. See, this is cross. Okay, d square f by dx1 dx2, d square f by dx2 dx1. Okay, so like this it is Hessian matrix. Okay, so find the individual value over here. First find the df by dx1. So calculate df by dx1, you will get a 1 plus 4x1 plus 2x1, sorry 2x2. Okay, so likewise you have to calculate d square f by dx1 dx2 to differentiate this with respect to x2. Okay, so you will get as 2 only, 2. So now calculate d square f by dx1 square, differentiate this again with respect to x1, you will get 4. Okay, no, this is 4. Okay, so likewise you have to differentiate for all the values and put the value in this Jacobian, that is Hessian matrix. Okay, now you have to find this Hessian matrix inverse. So how to find this? See, you first have to do 1 upon this cross value, that is what it is, 4 into 2 minus 2 into 2, like how you solve the matrix, that only. So you have to take the inverse of that and you just swap this 2 value. Okay, these 2 values should come in negative and swap this 2 value, 2 and 4. This 2 and 4 should be swapped and take negative of this 2 value. Okay, so this is the inverse of the Hessian matrix. Okay, so like that only you have to take the inverse. And now finding the G1 equal to df by dx1 df by dx2 at x1, that is equal to 0 0. You will put the value of x1 and x2 as 0 0, you will get this. Okay, then how to find x2? X2 is equals to x1 minus Jacobian inverse G1. Take care of this minus in between, this one. Take care of this, it's not plus, it's minus. Okay, so remember the formula accordingly and put all the values. X1 0 0 minus Jacobian is what? Jacobian you get as Jacobian inverse as this one. Put here G here, then you will get all the values. Alright, now see how to solve this. This is the matrix multiplication. So take the row from here and column from here, and row into column you can do. Okay, so 1 by 2 into 1, okay, plus this minus 1 by 2 into minus 1, and minus 1 by 2 into this one plus 1 into this minus 1. Okay, so like that it is solved. So x2 we will get here. Okay, so now find G2. G2 how can you find? At x2, that is equals to, put all the values here, you will find G2. Now find x3 is equals to x2 minus, same you have to find with the same procedure. Okay, so now you can see this, x3 is equals to x3, x3 is equals to x2, because if you do Jacobian 1 inverse into G2, G2 here is 0 0, so it will also become 0, so you will get the value of x2 only here. Okay, so when you get the value of x2 the same as x3, then it is the optimum point. What is the x2 is the optimum point. Okay, so this is the answer for this question. I hope you understand. You just have to remember this and you have to remember the steps what we are doing. First the Hessian matrix we are solving, putting all the values. Then G1 we have to calculate this G1. Then we have to calculate for this value, and again the same process we have to repeat. All right. Now next move for the next question. So this is the question, you can solve, you can practice it, so you will be cleared with this concept. Okay, so next is the theoretical concept, mini batch gradient descent and stochastic gradient descent and gradient descent actually. So explain the terms gradient descent, mini batch gradient descent and stochastic gradient descent. This is all the previous year questions. See, the gradient descent. It is the optimization algorithm used to minimize a loss function by iteratively moving in the direction of steepest descent, which is opposite to gradient of the function at the current point. Okay, so it's an optimization algorithm used to minimize the loss function. Okay, by iteratively moving, like we are performing the iteration 1, iteration 2, and we are seeing for the values that are closer to the given value. Okay, so same it is written here. You have to just read. It updates the model weight by calculating the gradient of the loss function and adjusting the weights according to the reach, the local minima, like we are doing for the x values, x1, x2 we are finding. The same here it is. Now the second is mini batch gradient descent. It divides the entire data set. See, the name itself suggests it's a mini batch. So the whatever the data set is, we have to divide it into 1000 records or each, like we have to divide it into multiple records. Okay, then the algorithm computes the gradient of each mini batch and updates the batch after processing each batch. It helps reducing memory errors and speed up. It helps reducing memory errors and speed up training, but leads to zigzag path towards a minima due to noise in small batches. See, a noise, small batches can generate some noises. Okay, so because of that it has a zigzag path. Okay, so just read it, and same you have to write in exam also. Third one is stochastic gradient descent. It updates the model's weight after computing the gradient from a single random data point rather than either entire data set. Okay, so what it will do is it will update the model weight after computing the gradient from a single random data. Okay, it will not see for the entire data set, which these two are doing. Okay, this is separate, this is dividing the data and this is seeing all the data set. But stochastic gradient descent won't do this. It will update the model's weight as it moves further. Okay, as it iterates into the data set. Okay, making training process faster, since it is doing in all it is updating weight in every iteration. The process is faster and more scalable for large dataset. Okay, since updates are noisy due to being based on individual data points, the path towards the minima can be more fluctuating or zigzag in the nature. So it's the same, like updates are noisy due to we are iterating it at the we are updating weights at the every iteration. Okay, so it can be noisy when the large data set we have, and the path towards the minima can be more fluctuating and it can be zigzag. Okay, so this algorithm is different question. Okay, so this for this question you have to write only this much. So algorithm is for different question. Algorithm can also be asked in the examination. The algorithm for gradient descent is, what the purpose of this gradient descent? To find the minima of a function by iteratively updating weights using the entire data set. Okay, so this is the purpose of this gradient descent algorithm. So how to proceed with this? See, step 1 is to initialize weight x, repeat until convergence. It means when the value what we need, that is similar to the that calculated value, compute the gradient over entire data set, update weights, x new is equals to x minus x eta delta fx. Eta is the learning rate, obviously. Then see here, eta controls size of the steps, that is learning rate. So this is the algorithm for this gradient descent algorithm. Okay, so second one is mini batch gradient descent algorithm. Purpose of this is weight using small batches of data to balance computational efficiency and convergence stability. What it will do, it will divide the data set into batches of size m, then initializes weight to x. Okay, for each epoch. Epoch means what? For updating, after updation of weight in every iteration, when iteration iterates for all the data set, when it finishes the data set and when it updates the value, that complete cycle is epoch. Okay, then for each epoch shuffle the data set, then this is optional. And for each mini batch compute the gradient separately, update weights, and then repeat until convergence. Repeat until you get the close value. Okay, so that is the whole algorithm takes. Now move for the third one. The third one is stochastic gradient descent algorithm. What is the purpose of this? To update the weights after each individual data points, making it suitable for large data set. Okay, so let's see the algorithm. Initializes weight x, repeat for each epoch, shuffle the data set. For each data point xi in the data set, compute gradient delta fx xi based on single data point. Update weights, that is x new is equals to x minus eta delta fx xi. Okay, so just see the algorithm, and this is important question, so just understand it. Okay, I hope you understood well. Let's move for the let's move with the next question, that is difference between stochastic gradient descent and mini batch gradient descent method. So we are finding the difference based on this update frequency, size of data, computational speed, stability of updates, memory requirement, and suitability. Okay, so what is update frequency? For stochastic gradient, it updates after each individual data point, and for mini batch, it after each mini batch of a data point. Okay, so it updates weight after each data, and for mini batch, since it divides the entire data set into the batches, so once the batch is complete, then only it updates the weight. Okay, then according to size of data used per update, this is one data point and this is small batch. Okay, computational speed, it is slower due to many updates, more frequent computational, and it is faster than this one, fewer updates per epoch. Okay, stability of updates, this is noisy and this is smoother because completing a gradient and then updating it, so this is smoother. All right, then memory requirement, that is minimum memory is required for this one, because it's updating weight in every iteration. It's not need to put any value in the memory. Okay, so for here, since it going to all the batches separately and updating the weights after a batch is finished, so it need to store all the intermediate values, so the memory requirement is moderate. Okay, suitability, this is suitable for larger data set and this is suitable for large data set, balance between the speed and stability where we need. Okay, so just read this, and with this I think this module is finished. So I hope this module is clear to you all. I will upload this PDF in the description. Just have a look in this PDF. Thank you all.